Hey guys, let's talk about Kubernetes master first. So the master is responsible for exposing the API, scheduling the deployments, and managing the overall cluster. The definition of Kubernetes objects such as pods, replica sets, and services are submitted to the master. Based on the defined requirement and availability of resources, the master schedules the pod on a specific node. The node pulls the images from the container image registry and coordinates with the local container runtime to launch the container. etcd is an open source distributed key value database from Core OS, which act as a single source of truth, which is SSOT, for all components of the Kubernetes cluster. The master queries etcd to retrieve various parameters of the state of the nodes, pods, and containers. This architecture of Kubernetes makes it modular and scalable by creating an abstraction between the application and the underlying infrastructure. Now what we will do is we will talk a few things about the principles. So coming on to the principles, Kubernetes is designed on the principles of scalability, availability, security, and portability. It optimizes the cost of infrastructure by efficiently distributing the workload across available resources. This section will highlight some of the key attributes of the Kubernetes. First is workload scalability. Applications deployed in Kubernetes are packaged as microservices. These microservices are composed of multiple containers grouped as pods. Each container is designed to perform only one task. Pods can be composed of stateless containers, of stateful containers, or stateful containers. Stateless pods can easily be scaled on demand or through dynamic auto-scaling. Kubernetes 1.4 supports horizontal pod auto-scaling, which automatically scales the number of pods in a replication controller based on CPU utilization. Future versions will support custom metrics for defining the auto-scale rules and thresholds. Hosted Kubernetes running on Google Cloud also supports cluster auto-scaling. When pods are scaled across all available nodes, Kubernetes coordinates with the underlying infrastructure to add additional nodes to the cluster. An application that is architected on microservices, packaged as containers, and deployed as pods can take advantage of the extreme scaling capabilities of Kubernetes. Though this is mostly applicable to stateless pods, Kubernetes is adding support for persistent workloads such as NoSQL databases and Relational Database Management System, which is RDBMS. Through the pet sets, this will enable scaling stateless applications such as Cassandra clusters and MongoDB replica sets. This capability will bring elastic, stateless web tiers and persistent stateful databases together to run on the same infrastructure. The other feature is high availability. Contemporary workloads demand availability at both the infrastructure and application level. In clusters at scale, everything is prone to failure, which makes high availability for production workloads strictly necessary. While most container orchestration engines and PaaS offerings deliver application availability, Kubernetes is designed to tackle the availability of both infrastructure and application. On the application fronts, Kubernetes ensures high availability by means of replica sets, replication controller, and pet sets. Operators can declare the minimum number of pods that needs to run at any given point of time. If a container or pod crashes due to an error, the declarative policy can bring back the deployment to the desired configuration. Stateful, stateful workloads can be configured for high availability through pet sets. For infrastructure availability, Kubernetes has support for a wide range of storage backends coming from distributed file systems such as Network File System (NFS), Gluster FS, block storage devices such as Amazon Elastic Block Store EBS, and Google Compute Engine Persistent Disk, and specialized container storage plugins called Flockers. Adding a reliable average storage layer to Kubernetes ensures high availability of stateful workloads. Each component of a Kubernetes cluster, etcd, API server nodes can be configured for high availability. Application can take advantage of load balancers and health checks to ensure availability. The other feature is security. Security in Kubernetes is configured at multiple levels. The API endpoints are secured through transport layer security, which is TLS, which ensures the user is authenticated using the most secure mechanism available. Kubernetes cluster has two categories of users: service account managed directly by Kubernetes and normal user assumed to be managed by an independent service. Service account managed by the Kubernetes API are created automatically by the API server. Every operation that manages process running within the cluster must be initiated by an authenticated user. This mechanism ensures the security of the cluster. Application deployed within a Kubernetes cluster can leverage the concept of secrets to securely access data. A secret is a Kubernetes object that contains a small amount of sensitive data such as password, token, key, which reduces the risk of accidental exposure of data. Username and passwords are encoded in base 64 before storing them within Kubernetes cluster. Pods can access the secret at runtime through the mounted volumes or environment variables. The caveat is that the secret is available to all the users of the same cluster namespace. Next is portability. Kubernetes is designed to offer freedom of choice when choosing operating systems, container runtimes, processor architecture, cloud platform, and paths. So these are the few features and points which needs a brief detailed introduction. In the next lectures we would cover a few more items before going back to some codings and related things. Thank you.